Continuing our minor foray into chapter 16, we're going to start the topic of entropy. So, first thing we're going to do is define entropy. We will explain the relationship between entropy and the number of microstates, which will also require that we define the number of microstates. And we will predict the sign of entropy changes in chemical and physical processes. So, what is entropy? Entropy, or delta S, describes the change in energy from the way that matter and energy are organized before and after a process. Another way of putting this is that it is the measure of disorder in a system. Delta S is equal to dq reversible over T. That is its definition. That little d there stands for derivative. In other words, taking the slope. Q is heat, just like it always is for thermo. Reversible in thermodynamics means that you take itty-bitty steps and you can go forward or backward and it doesn't make a difference. It's a reversible process. In realityville, there is no such thing as a perfectly reversible process, but for our math, that's what we're going to talk about. And T here is always in Kelvin. I hope that you guys remember that from the last time we talked about thermo. T is always in Kelvin. One more time, temperature is in Kelvin. Now, they discovered this when they were doing research into steam engines, and they found out that you have to have a hot side and a cold side in order to get work out of the engine. And that may seem like a kind of strange concept, but can you imagine powering a boat by dropping a piece of metal into the water and trying to suck energy out of the water? That doesn't make sense, right? But you could imagine that if you had something that was heating on one side, it causing a turbine to go if you have something dropping into the water that's cold. Hot side and cold side necessary to pull out work. Okay, moving on.
Sweeties.
Sure, honey, go ahead.
Hello, sweeties.
All right, so what is a microstate? A microstate is a specific configuration of all the locations and energies of matter, and that could be atoms and or molecules, that make up a system. So, entropy is equal to K times the natural log of W, where W is the number of microstates that are possible, and K is Boltzmann's constant, 1.38 times 10 to the negative 23rd joules per Kelvin. Delta S is equal to K times the natural log of the final number of microstates over the initial number of microstates. Therefore, if WF, the final, is greater than the initial, delta S is positive. So if things spread out more and get more chaotic, delta S is positive. If WI is greater than WF, the initial state is more chaotic than the final, then it will be negative. So if you organize a system, delta S is negative, and if you let it go all over the place, delta S is positive. So let's talk this through a little bit further. Let's take an example out of the textbook. So let's say you have 4 molecules in 2 chambers. General probability for how many different microstates you would have in this situation is n to the n, where lowercase n is the number of boxes and capital N is the number of particles. We have 2 boxes, we have 4 particles, 2 to the 4th is 16. So how do we get this? We come up with this picture. We have the option where all of the molecules are on the left. We have the option where all of the molecules are on the right. We have different ways of organizing 3 and 1 in the boxes. And then we have different ways of organizing 2 and 2. And we can define how probable each of these are by taking the total number of boxes, or sorry, the one that we're interested in, and putting it over the total number of boxes. So for A, that would be 1 in 16. For B, that would be 4 in 16. And for C, that would be 6 in 16. The most probable state that the system will be in is C. It will likely be in that mixture of 2 and 2. So let's calculate a change in entropy. Given the system pictured below, calculate the change in entropy. And this is just a remix of what we had in the previous slide, but it'll work for our purposes. So we first remember that our delta S equation is delta S is equal to K natural log of WF over WI. Please stop. Okay, so in the beginning we have one single microstate, and then at the end we have 4 possible microstates. So we went from 1 to 4, and we go ahead and plug in those numbers. And when we do, we find that delta S is equal to 1.91 times 10 to the negative 23rd joules per Kelvin. Now, I don't know about you, but that seems like a really tiny number. But then you have to remember that in a laboratory type system, we're normally dealing with moles of stuff, right? We weigh out moles of things, and that is 6.02 times 10 to the 23rd of atoms or molecules. So delta S times K is going to end up being a decently large number in most of our normal everyday situations. Okay, so what can this concept of microstates being related to entropy tell us? If there are more possible configurations or possible microstates of energies and matter, then entropy is going to be greater. So, for example, let's start with solids, liquids, and gases. A solid has a very well-defined structure. It doesn't move around a lot, so it has a very low entropy. A liquid, those molecules can move and they can slide around each other, so it has a greater entropy than a solid. And a gas, all of those molecules are free agents, and they can move wherever they want to in the entire size of the container. So a gas has the greatest amount of entropy by far. So entropy of a gas is much, much greater than the entropy of a liquid, which is greater than the entropy of a solid. And that's just by virtue of what those things are. All right, so let's think about the implication of having a higher temperature. If we have a higher temperature, we can remember the Maxwell-Boltzmann distribution for temperature, and we know that as we raise the temperature, we have a wider distribution of speeds for our molecules, which is more entropy. And on this particular plot, we have 3 things marked on each temperature. The 1 refers to the highest probability speed of the molecules. The 2 refers to the average speed of the molecules. And the 3 refers to the root mean square speed, which is the temperature of the molecules. So you can see that these are slightly different, and they shift toward the right as we go onward. But hopefully that all makes sense. As we raise the temperature, we've increased the variety of speeds that we can give the system, so there's more energy states, therefore more entropy. Okay, so here's some other ones that don't really require a graph or a picture, because they're pretty simple concepts. First one, more moles of stuff equals more entropy. Why? Our general thing that said that the number of microstates was equal to the number of chambers raised to the number of molecules. Okay, so number of places you can be raised to the number of molecules. So if you increase the number of moles, you're increasing the N. You're exponentially increasing the number of microstates. That is a lot. If you have more atoms on a molecule, then that molecule will have more entropy. And the book says it's beyond the scope of this book to talk about why that is, but basically molecules with more atoms can move in more ways. And we're going to leave it at that. Okay, heavier atoms have more entropy by virtue of having more electrons. Simple as that. They can go through more energy transitions. Mixtures have more entropy than compounds, and that completely makes sense, because if I mix 2 things together, there's way more ways that I can organize the molecules if I have 2 different types of things in my mixture. Okay, so mixtures have more entropy than pure compounds. All right, so let's try to predict the sign of delta S. Let's say we were precipitating silver chloride. So we're going from an aqueous solution, which is a mixture, to a solid. And we know that solids have way less entropy than liquids. And also we're going from 2 particles down to 1. So that is going to have a very negative delta S. We're drastically reducing the entropy of the system. Now let's say we're melting ice. So we're going from a solid to a liquid. We know that a liquid has more entropy than a solid, so this is positive. Cleaning up a mess. That is going to reduce the number of possible microstates in a system, and so that will be negative. And if you were to raise the temperature of your system, you would increase the variety of energies possible, which would give you a positive delta S. Okay, so hopefully you've got down the basics of this idea, what a microstate is, how it's related to entropy. Give it some practice, and I hope that studying is going well for the exam next week. All right, I will see you on Monday. Let's summarize what we found out. Entropy, or delta S, describes the energy change from the way matter and energy are organized before and after a process. Delta S is equal to dq reversible over T, where Q is heat and T is temperature in Kelvin. S is equal to K, which is Boltzmann's constant, times the natural log of the number of microstates given by capital W. Change in entropy is equal to K times the natural log of the final number of microstates over the initial number of microstates. And finally, K, Boltzmann constant, is 1.38 times 10 to the negative 23rd joules per Kelvin. The entropy of a gas is much, much greater than the entropy of a liquid, which is greater than the entropy of a solid. Higher temperatures have more entropy due to the distribution of speeds. More atoms, moles, and electrons will have more entropy, and mixtures have more entropy than pure things.